All right, it is 12:02 and we'll begin the webinar. Welcome everybody to this second webinar in our Innovation Showcase Fall series entitled Quantification and Prediction of Greenhouse Gas Emissions from Wastewater Treatment Plants in partnership with Toronto Metropolitan University. Before we start the webinar, just like to say a few words about the Ontario Water Consortium. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, supported or created more than 350 industry jobs, and advanced nearly 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before introducing today's webinar, we also hope that you'll join us again for our final webinar in this fall series. On October 8th, the University of Windsor will present interdisciplinary approaches for restoring and protecting freshwater ecosystems with a focus on biodiversity conservation across the Great Lakes Basin. I will drop the registration link for that webinar in the chat in just a moment. All sessions are free to join, and please also note the QR code here that you can use to subscribe to the OWC newsletter. Now, I'm very pleased to introduce Dr. Elsayed Elbeshbishy, Professor of Civil Engineering at Toronto Metropolitan University, to begin today's webinar entitled Quantification and Prediction of Greenhouse Gas Emissions from Wastewater Treatment Plants. Dr. Elbeshbishy will provide an overview of the project and highlight the technical challenge in quantifying emissions. Following Dr. Elbeshbishy, we will hear from Dr. Ahmed Elsayed, who will present a case study on methane emissions, and Marwan AlSaleh, who will share a full-scale case study on nitrous oxide emissions. Elsayed, the floor is yours.
Thank you so much, Robert, and thank you so much for everybody that is joining us in this webinar, and I hope that we're going to have a great time together. Okay, let me share my screen and tell me if you can see my screen.
We can see your screen.
I'll just make it in a presentation mode.
Yeah.
Try to get the laser pointer, and here we go.
There we go.
So thank you so much, Robert, and really I would like to thank very much the OWC, not only for supporting this specific project, but for the overall supporting the R&D in general in Ontario. And this is not the first project that we collaborate together. We collaborated together with many projects in the past, and now we are working together in this specific project, which is focused on the greenhouse gas emission on a municipal wastewater treatment plants. And in this project, we didn't only focus on one sector, but we are covering all the sectors, starting from the collection system. So we are studying the greenhouse gas emission on the collection system, and also the greenhouse gas emission on the mainstream, which is coming from the wastewater treatment train, and also the greenhouse gas emission coming from the sludge management part. So in general, we are focusing on the sewer network and wastewater treatment processes and sludge management, and we measuring both, or we're looking for both methane and nitrous oxide. And the main sources for methane emission, this is what we thought, by the way, at the beginning, when initially thought about this project, to put the things together and put the research question, we were thinking that the methane is mainly coming from the collection system, primary clarifiers, anaerobic digestion, and the sludge storage. However, you're gonna see today, based on our experience, there are some other stuff that we didn't know about them before, but from this project, we highlighted some of those sources for the methane emission that typically we don't consider in our mind. Same thing for nitrous oxide. When we planned for that specific project, we were focusing, oh, nitrous oxide is going to be from those wastewater treatment facilities that is implying the nitrogen removal, and they have the nitrification, denitrification process was the focus, and said, okay, what if we tested a facilities that is not designed for nitrogen removal? What is going to happen? And you will see some surprises today from this specific experience that we had in this project. So I will tell you what is the research question that we put at the beginning, and this is what we want to really understand at the end of this project. So from the methane emission perspective, our target was to get to know what is the best sensing technique for methane emission measurements. Because as you know, we have many sensing techniques or methods to monitor the methane emission. So which one is better to use? Is it the ground sensing or the aerial sensing or what? And if we applied multiple sensor or different sensing method, and what we call it multi-level, from the ground sensor to the aerial sensor, even using the computer simulation, and try to get a correlation between those sensing methods. That was another thing in order to, oh, can we use one to replace another? And what is the best method on detecting the methane emission on the wastewater, specifically on the wastewater treatment plants? And same thing as you know, if we know the methane emission and we know the sources, we can mitigate that and we can reduce the emission. That's from engineering perspective, I would say, sorry to say that, but I say it's an easy part. But the question is, are we confident about the accuracy of the measurements that we are getting? Are we confident about those numbers? And we did a quick literature review based on the data reported in the past, and we see significant variation was the methane emission when it's measured versus what is calculated based on the emission factor on the IPCC, the most common one for theoretical methane emission from facilities. And that variation, sometimes when you measure it, it's 10 times was compared to the theoretical one, and sometimes it's 1/10. So it's significantly varied. So what are the main factors that impacting that accuracy that we should really focus on them? And we were trying to estimate the plant-wide methane emission and compare it with what we call it the theoretical methane calculation using the emission factor reported by the IPCC, and try to see, okay, how far is the calculated theoretically versus measured on a couple of case studies on Canadian facilities. And we want to get what are the strengths and weaknesses for each sensing technique, because this is one of the very critical things, to have a reliable and accurate number so you can but a good strategy for mitigation. And plant-wide model, there are some effort in the literature, and when we reviewed that, we found that a lot of assumptions that happened when you are calculating the methane emission using the plant-wide model, and said, okay, let's see what are the challenges and how can we add a little bit improvement to that kind of plant-wide modeling for the methane emission. And when it comes to the nitrous oxide on the other side, okay, said let's compare between the methane emission, the nitrous oxide emission from non-nitrogen removing facilities compared to the nitrogen removing facilities. If some facilities has BNR or nitrogen removal versus none. What we call it for the non-nitrogen removing facilities, we call it unintentional nitrous oxide emission, or sometimes we call it unoptimized nitrification. And we want to also study what are the variables and the factors that impacting the nitrous oxide emission. And as you know, there are three pathways for the nitrous oxide emission. So which pathway that can happen during the operation of the facilities, and what parameter that trigger one pathway versus the other. And again, we are now in the era of the AI and modeling, so we cannot consider that. So we develop a mechanistic and machine learning model for nitrous oxide, and ultimately our hope is to come up with a hybrid model for the nitrous oxide emission, because there are some parameters that is a lot of facilities that they are not measuring. So the idea here is to use the machine learning model, or what we call it the soft sensors, to predict some of those parameters that are not frequently measured on some facilities. And honestly, in this project, we are so proud to have this type of work when we said, oh, let's monitor the greenhouse gas emission on the collection system. And I would say this is first of its kind sewer physical twin that we have in North America. And we are trying to understand what are the variables that is trigger the methane emission on the collection system. And this is one step toward this, developing a digital twin for the collection system. And again, modeling is a big component of our project. And we both investigate the mechanistic model and the data-driven model, and we combine them for the hybrid model and apply the modeling. And even that modeling is a big component. We can maybe arrange with Robert and Rahim to have a separate session about the modeling later on or early next year or so. So what is unique about this specific project that we are so proud to have this project is, first, is the powerful collaboration that we have. As you see that we have 16 partners, including municipalities, industries, the research institution, and that showed the importance of the topic itself. So greenhouse gas emission is a very important topic nowadays, and we have many collaborators and partners with us in this specific project. And that's why you can see that the team that is working that project is very diverse. So have a diversity of expertise, starting from the collection system, the wastewater, the sludge management, the modeling, both mechanistic and artificial modeling, even the remote sensing and many other expertise. So that's a very powerful team that is working towards one goal, to better understand the greenhouse gas emission on or from the wastewater treatment plants. So what I want to say that highlight that we have three things that is first time to happen in a research domain. That is first study to have that we call it the multi-level detection of methane. And some research or some work even by the industry, they did already maybe a couple of methods on detecting methane, but for this specific project, we have 4 levels in addition to the simulations. We have the ground sensor, we have the OGI camera, we have the drone, we have the airborne, and we have the satellite in addition to the both mechanistic model and the data-driven model or machine learning model. And as I mentioned, this is the first of its kind, the physical twin for the gravity sewer in North America. We're so proud to have that pilot sewer system. And we have 2 pilots, by the way, with different materials testing the greenhouse gas emission from the collection system under different conditions. And first step, trying to mimic what is happening in the reality. And trust me, it's quite challenging, but we are on our way. We are very close to there. And second thing, having that first plant-wide modeling trial using the hybrid model. We cannot ignore the powerful of the social media. And I'm a very guy that believe on the social media, that we say that, okay, we want to increase the public awareness. That's why we created a lot of events, a lot of material to inform people about the greenhouse gas emission. Even we reached to the TikTok, Instagram, we have YouTube channel. We generated some educational material in terms of videos and stuff. We visited the community center, the schools, to increase the awareness about the topic itself. So today we're just going to focus on one specific part of that project, which is a case study called greenhouse gas emission monitoring campaign that have been done in one of the wastewater treatment facilities here in Canada. And I'm going to leave the floor now to Dr. Ahmed Elsayed to give us throughout the methane sensing and quantification in wastewater treatment plants. So now I'll leave the floor to you, Ahmed.
Thank you, Elsayed. And I'm just going to say, it seems like Saad Ulhak has a question, but Saad, if you could just keep that question for the end of the session, we'll have a question and answer period at the end. So just make sure you remember your question and we'll deal with that at the end. Thank you.
Can you see my screen?
Yes.
Great. Hi, everyone. First of all, thanks so much, Dr. Elsayed, for laying the ground for my presentation about case study for using multiple sensing techniques in methane quantification from a full-scale wastewater treatment facility. So let's start with a quick overview about the agenda. So I'm going to go briefly through the background, motivation, main objectives, and site description, and I will allocate most of the time for sensing technologies and describing the process isolation and the overall emissions from the facility. So a quick introduction, as Dr. Elsayed mentioned, we have multiple innovative sensing technologies that are super critical for better detection and quantification for the methane emissions from wastewater treatment facilities. We have different types, including the stationary sensors, including ground sensors, mobile sensors, such as handheld camera, and aerial sensing, including drone and aircrafting. However, there is a clear lack in the literature about applying multiple sensing technique within the same area on a full-scale wastewater treatment facility. And it's the most important point as well is highlighting the strengths and weakness points of each of sensing approach and how to complement everything together. So the main objective of this quick presentation is to walk you through the application of multi-level sensing technologies within a full-scale treatment facility and isolate the potential sources of emissions and quantify the plant-wide greenhouse gas emissions from the entire facility. So quickly for the site description, we have a Canadian municipal wastewater treatment facility with a typical configuration of wastewater treatment facilities with secondary treatment and primary treatment, beside anaerobic digestion systems and waste gas burners. The most interesting point within this facility is they have high organic loading rates and content, which can highly reflective on the greenhouse gas emissions, especially the methane. For the sensing techniques in this study, we have three sensing approaches. The first one is the ground sensors, and we call it like SOFI sensor. Second one is drone sensors, and third one is the handheld OGI camera. So for the ground sensor, we have that set of 4 months continuous monitoring that set based on 15 minutes interval. And for the drone sensor and handheld camera, we have a snapshot of intensive 3-day on-site campaign on the site. Starting with the ground sensors, we have right here the SOFI sensors. The typical formation of this one is with a metal base and metal post and mounted with a solar panel beside the box right here, which including the main components of the sensor. And this one was provided by Champion X. Inside this box, you can find like a battery, which can work for lasting for 12 hours, storage controller, and the most important part, which is the MOS or the metal semiconductor sensor that measure the transport and the methane concentration, and this fan to grab sample of air for analysis. So in total, we have 16 ground sensors were distributed along the over the facility, and we have, as I mentioned, 4 months of continuous data. And the main objective was to do like process isolation and identifying the methane hotspots. The second platform or the second technique is the drone sensors. We have 2 different sensors were mounted on the drone. The first one is called the OPLS sensor, Open Pass Laser Spectrometer, that can be used for quantification for the emissions in terms of flux or the plume itself. And second one for detection sensors, just to tell us whether there is fugitive methane at this area or not, using the halo OGI camera. And both of them are also provided by Champion X. So for the drone OPLS, it meets on a certain concept called the wind curtains. So for example, if we wanted to isolate this group of aeration tanks, so we have to fly downwind and upwind of the process itself, and from there we can subtract the difference between the two emissions, and from there we can identify how much was emitted from this process. So we did more than 50 wind curtains along the facility, trying to isolate each group of units, and from there we can determine the emission rate from each one. There is an example for the hollow OGI camera that we can see from the second detection sensor that was mounted on the drone. The green lines right here, or the green bloom right here, showing the methane, and from here we can see the emissions coming out from the waste gas burner, including the thermal and steam aspects as well. For the handheld OGI camera, we use the handheld Konica Minolta OGI camera that was provided by Brown Caldwell, and we can see from here how they were able to quantify the emissions using the Konica Minolta OGI camera from the waste gas burner. I don't know what is, oops, why it's not working. Let me, yeah, here we go. So we can see from here the thermal image showing the thermal effect of the plume, and high sensitivity showing the steam interference with the atmosphere. So let's jump to the process isolation, and for the sake of time, I'm going to show just two processes, the anaerobic digesters and the aeration tanks. For the anaerobic digesters, we can see like a time series for 4 months for the concentration of methane ppm using the ground sensor around the around the anaerobic digesters, and we can see that the average is 8.9 ppm with some spikes at 45, 50, up to 60 ppm. For the drone using the OPLS sensors, so let's have this one, the anaerobic digesters. The upwind methane emissions were around 1.2 kilogram per hour, and downwind was around 10 kilogram per hour. And when we subtract the downwind from the upwind, we can find that the anaerobic digesters are emitting around 9 kilogram per hour in terms of methane. Using the handheld OGI camera, we can see some fugitive methane from the relief hatches from the valves, as you can see right here, the small plumes right here. And in general, although we have some emissions, but they are not super high because they have fixed roof digesters and they always refabricate the digesters on a scheduled maintenance process. Second process is the aeration tank, and compared to the anaerobic digesters, we have 11.4, which was 8.9 for the digesters, and we have a lot of spikes for the methane concentration up to 120, which is almost double the spikes that were allocated within the anaerobic digesters, indicating that the aeration tanks are emitting a lot compared to the anaerobic digesters. And we can see from the OGI camera, we can see the plume coming out from the open hatches within the aeration tanks. And our justification for such high emissions is probably due to the coarse aeration, low sorbent oxygen concentrations, and poor mixing conditions within the aeration tanks. So in general, before we jump to the plant-wide emissions, so let's have a look on two heat maps for June of 19th of June and 26th of June. And for here, we can see the distribution of methane concentration in ppm using the ground sensor. You can see right here, ground sensor number 3 and 4 and 5 has the highest emission with between 12 to 15 ppm. But just 1 week after, we found like 3, 7, 11, 14 has high emissions with up to 19.2. Even for the low concentrations, which ranges right here from 9.3 to 13.5, it was ranging right here from 3 to 7. That means that we have methane everywhere, and we have alternation between the process in emitting the process according to the operational conditions and schemes right there. So in general, if we wanted to fractionize total emissions, so we will find around 40% of emissions coming from the aeration tanks, followed by primary treatment, 22%, waste gas burner, and surprisingly, the dewatering system and the anaerobic digesters are contributing by around 7% of the total emissions. So if we wanted to transfer these values into numbers, so we can see that the total emissions is around 1,400 kilogram per day, which is representing between 2 to 4% of the effluent COD. So although we have high concentrations in aeration tanks and the primary treatment, but at the end, it's representing around 2 to 4% of the influent COD, which is very comparable with values in literature that has up to 6 and 7% of the influent COD. So although we have some emissions, but it's still within the reported limits. So finally, if we wanted to compare the emissions from the methane with the emissions from nitrous oxide, which Marwan will be talking about in a few minutes, so we can find right here is the methane has almost 83% contribution for the total greenhouse gas emissions compared to 17% for nitrous oxide, which is not really common. All people always think that nitrous oxide is more dominant in wastewater treatment facilities, but according to this study, we can say that it highly depends on the operational conditions, influence characteristics of the facility, and compliance element for each facility. So in conclusions, we assessed the performance of different sensing techniques. We found that OPLS drone and held camera were the most effective techniques to find reasonable quantification of methane. And it's very important to integrate multiple sensing approach. And from wastewater treatment perspective, we can find that all of them are emitting methane, especially the aeration tank and the primary treatment. On the other hand, surprisingly, the anaerobic digesters didn't emit a lot within this one, which means that the greenhouse gas emissions are highly dependent on different factors, especially when the methane contribution is much higher compared to nitrous oxide. So I hope that I stuck to the 10 minutes limit, and I will leave floor for Marwan AlSaleh to give a brief presentation about the nitrous oxide campaign. Thanks so much.
Thank you, Ahmed. Let me share my screen. Okay, so hello everyone. This is Marwan, PhD candidate at TMU, and today I'm going to present nitrous oxide emissions in full-scale wastewater treatment plant. So let me just go through the agenda. So first we have background, and then I have 2 case studies. I hope I can cover them both in the given time. And then I will share some results from these 2 case studies. So first thing, in the background, why N2O matters. So there is too much reasons why we need to study N2O emissions. First thing, N2O is a potent gas. It's 300 times stronger than CO2 in contributing to global warming. And also, it can stay in the atmosphere up to 100 years. And also, it is a depleting gas to the ozone. So this is from the environmental side. From the production side of N2O emissions, there is a lot of factors that can affect N2O emissions production, especially in a full-scale wastewater treatment plant, because you cannot control all the factors. We don't have that luxury to optimize all the factors in wastewater treatment plants, especially the loading rates, the flow that comes to the plant, also the structure, like it's already there, the infrastructure. So we have very limited options to be optimized and changed. For example, the DO, and we can also change like the aeration basically to adjust the DO, and also we can change how the flow is going to, like how we distribute the flow into the tank itself. So what we did is we did 2 separate case studies, case study 1 and case study 2. So in case study 1 at the left, that was a learning journey for us. That was the first case study. We selected a conventional aeration basin. So it's basically meant for carbon removal, not for nitrogen removal. And then we tried to see if the conventional aeration tank, even if it's not designed for nitrogen removal, will we see some nitrous oxide emissions? And that was the case. We saw a lot of N2O emissions. I will share the results in the next few slides. So in that case, we tried to change the feeding strategy only. So we kept everything the same. Basically, we did not change the aeration flow rate. We did not change the DO. Like we did not try to change the DO, of course. And we did not change the flow as well. So we only changed how we feed the system. Are we feeding step feed? Are we feeding semi-block flow or block flow? I will share more details about this. And also we have case study 2. and we went for BNR system. So basically, it's designed for nitrogen removal, full nitrification and denitrification systems. And we saw that, or we wanted to study, even though this system is designed for nitrogen removal and it's optimized to do so, would we still see some nitrous oxide emissions, and what are the main factors that affect this nitrous oxide emissions? So we tried to see the DO strategy. So basically, it means how we are controlling the air that goes into the tank, because basically the main step in the nitrogen cycle is transforming the NH3, which is ammonia, into other species, and that's how the cycle begins. And all this depends on the nitrification pathway. So basically, we tried three different things. We tried high fixed DO, and then we tried to lower the high fixed DO into a little bit, like we tried to cut from the high fixed DO into a little bit lower DO, and then we tried ABAC, which is ammonia-based aeration control. So let me share a little bit about phase 2. So in phase 2, we have this specific tank. So it's a BNR system. It's designed for nitrogen removal, and we have 9. This is a top view of the tank. We have 9 cells inside the tank. The first 4 from cell 1, 2, 3, 4. This is anoxic anaerobic. There is no aeration inside, and the mixing is done by a big mechanical mixer only. And from cell 5 into cell 9, there is aeration inside, and we have fine bubbles diffusers. So we try to change the DO basically from cell 5 to cell 9. And also we installed 2 N2O liquid sensors, which is the Unisense that you can see on the left side of the presentation. So you can see this is the controller, and we have the port, which is the sensor that can detect the liquid N2O concentration inside the reactor itself. So we included 2 sensors, one at cell 4 to detect any emissions that's produced through the anoxic zone, which is denitrification, and also we included one at cell 7 to see if there is any emissions comes from the nitrification thing. So basically, the location of these 2 was based on 2 things. First, the historical data. We already have the historical data for the plant for like 2-3 years, and we analyzed this data, and we conducted that the highest nitrification removal, or the highest ammonia removal, is happening between cell 5 to cell 7, and I will show you later on these results. So that's why we thought that including the sensor at the highest removal would result in highest emissions, if any. Same thing for cell 4. We tried all the cells. We tried to move the sensor from cell 1 to 2 to 3 to 4, and we tried to profile the N2O emissions, and we found that the highest at anoxic zone is cell 4, and the highest at aerobic zone is cell 7. So we went from there, and then we to confirm this and try to, I would say, explain why we got this N2O emissions, or if any. We tried to take a grab sample from cell 2, cell 4, and cell 7, and cell 9, and we also took samples from the influent of the plant, and also the final effluent and RAS as well. So just one thing to mention, we have 3 gates for this specific tank. We have gate 1 at the beginning of cell 1, gate 2 at the beginning of cell 2, and gate 3 at the beginning of cell 3. And one thing to note is we have a nitrified mixed liquor all the way from cell 9 to cell 3 for denitrification purposes. So we took a grab sample, as I mentioned, and we do test for pH, temperature, DO, total nitrogen, NO3, NO2, and NH3. Also, we did soluble phosphorus, TSS, VSS, and soluble COD as well. So regarding system performance, first thing, this is the achieved DO. So this is what we got actually from changing the aeration strategy. So at the left, this is the normal high DO. This is how they normally operate the plant. So basically at cell 5, because this is the beginning of aeration phase. So at the beginning of cell 5, the average was 2.7 milligram per liter as a DO, and at the end of cell 9, it was like 1.2. When we move to ABAC, and by the way, a normal high fixed DO, it's fixed DO. So basically, they don't change the aeration. So they basically fix the aeration regardless of how much ammonia they have or how much flow they have. So they try to fix the DO levels regardless you have ammonia or you don't have ammonia. For ABAC, I would say it's a smart option where you basically aerate based on the ammonia levels you have. So they have ammonia sensor at the beginning of the tank, and they have ammonia sensor at the end of the tank, and they basically do feed based on feed forward and feedback based on the sensor. So whenever you have high ammonia in the beginning, like high concentration and high flow, you basically have high ammonia loading rate as a mass. So that where they decrease, or that's where they increase the aeration to have more DO available for. They have more DO available for the bugs basically, or the microorganisms, to do the full nitrification cycle. So when we moved to the ABAC, the average was 2.3. So we had a cut of 0.4 mainly in cell 5. And when we moved to cell 9, there was almost the same. But on average, we had a cut like between 0.5 to 0.1. And when we moved to low fixed DO, so we tried to fix the DO on a lower, I would say, values. So instead of 2.7, we tried 2 at the beginning of cell 5. And instead of 1.2 at cell 9, we tried 0.8 at cell 9. Let's see how this affected the results. So first thing, the ammonia removal of the system, and this is based on cell 4 as our reference. So basically at cell 7 in the normal operation, 80% almost of the ammonia was removed. So basically like almost like 80%, which is like the majority of ammonia was removed between cell 5 to cell 7, as I mentioned in the previously. Same thing was happening in the ABAC. So basically we did cut the aeration, but nothing happened to the removal efficiency. So it did not affect the removal efficiency, even though we decreased the DO and we decreased the aeration as well. So at the end of the secondary effluent, almost 89% was removed in the normal, and almost 97% was removed at the ABAC. While if we compare this to the lower DO we tried, basically the removal efficiency was decreased by almost 30% at cell 7. So instead of having 80% of the ammonia removed, we had 53. And at the end, it was like almost 90%. So there's a decrease almost like 7 to 9% in ammonia removal overall. So if we try to link this with the DO or with the nitrous oxide, so basically this is the raw data. This is the liquid concentration. You can notice that in both normal and ABAC, we have basically the same trend. And this is the diurnal pattern, by the way. We start with 12 a.m. in the morning, and we end up with like 10 or 11 p.m. So basically, whenever you have peak flow, you have a peak in nitrous oxide emissions. And whenever you have low flow, you have low emissions. If we compare this to the airflow rate, which was cut by 20% when we moved from normal to ABAC, and was cut by 32% when we moved from normal to low emissions. And also, if we try to convert these two, which is the raw data with the airflow rate, into the N2O emissions, which was like calculated and to be emitted into the atmosphere, we noticed that the average mass flow rate for the high DO was 0.39, and for the ABAC was 0.35, which is almost like 10% reduction. And we noticed it's 0.216 kilogram as N2O per hour for low DO, which is like almost 44% reduction. This is the effluent, or this is the emission factor for 3 phases. It's still lower than the IPCC emission factor, but the fact that when we moved from high DO to ABAC, the emission factor was reduced, and also the nitrous oxide was reduced as well. The airflow was reduced, so we basically saved energy, and the performance of the ammonia was the same. So we did not lose any performance in the system. So it's still performing at very high removal efficiency. So at the end, because I think the time is finished. So at the end, basically, if we need to compare these 3, so we have trade-off between the performance of the system, the emissions, and also the energy saving. So I would say comparing these 3 together, the best was ABAC. So we reduced the emissions by 10%, we reduced the airflow rate by 17%, and we kept the same ammonia removal during the system. I think I don't have time to share the phase one, but if you have any questions, I can just do it at the end. Thank you.
Thank you, Marwan. We do want to leave a few minutes for questions here. It's a very insightful presentation from everybody. Thank you very much to all the presenters, and we'll now move into our Q&A section. We hope you guys stick around for your questions. We go a little bit over time, of course, for everybody who wants to ask a question, and perhaps we'll open the floor now. You can either post your questions directly in the Q&A. You could use the chat if you really want to, or you could, of course, raise your hand. I do remember Saad had raised his hand earlier, so I'm going to allow your mic, Saad, here. I've unlocked it. You should be able to unmute yourself and ask your question.
Hi, good morning, everybody. Great presentation, very, very helpful. First foray into really understanding the different methodologies for GHG. So I started off with one question, but I have three as the actual presentation went on, and it's around. The first one is very simple. What does it mean, Dr. Elsayed, when you were talking about a physical twin for a gravity sewer? What does that actually mean? I don't know if I've ever heard that term before.
Okay, just a term we use it to, if we want to mimic the actual gravity collection sewer, we want to make a pilot for that. So just we call it a physical twin. So we are trying, the first phase is we are trying to achieve what we are observing on the reality. Because it's not just, because this is a very tough, as you know, having a sewer pilot to mimic what is happening in the reality, that is the very challenging. And now we're trying to mimic the condition that is in the physical and the real case, and try to achieve the same emission that they are achieving with the condition that they are doing. So we are twinning what is happening, and then we're going to study the different conditions. So that's why we call it physical twin, trying to mimic what is happening on the reality.
Okay.
Now. Yeah,
I appreciate that. Thank you. The second question was that in the different methodologies that you were using for sensing, what was the overall variation between the different methods? Because you said which ones were the most efficient, but what was the highest range of variation between one method versus the other? And would you prefer using one? I mean, it seems like you prefer two methods over the other one. So how much was the variation?
Okay, so I would say the variation between, here is the difference between detecting and measuring or calculating the flux. So the variation between the OGI camera or the handheld OGI camera and the drone was not that significant. I would say we were able to get the same quantification for some specific processes that were measured using those two methods, was about maybe 50% variation, which is for us, very, very successful to have that kind of close variation. However, the major challenge that we had was the ground sensor, that we could not translate the emission concentration into a flux. When we did that, the variation between the calculated values from the ground sensor versus the drone, I would say more than 10 times. So now that's a big challenge that we cannot use. So the variation between the ground sensors versus the aerial sensor using the drone, for example, was significantly high. And that's why we did not rely on the ground sensors for calculating the flux more than identifying the hotspot. However, during that exercise, we learned a lot. So for example, there are some cases where the handheld OGI camera is very beneficial because it can go to some spots that the drone cannot detect. Same thing with the drone can reach out some location that the handheld cannot reach. Like the stack, for example, you can measure the emission from the stacks using the drone, while the handheld, it's very hard to go physically in there. The manhole and the valves and some cracks on the side that you can reach with the handle, you cannot monitor it with the drone. So we learned from that campaign a lot, even from designing the ground sensor. It's like not just putting it downwind or trying to put it as much as you can downwind the process. And even if you put upwind, no, it's not the case. And the big lesson that we learned from the first campaign, that is wind direction and wind speed are very crucial parameters. You have to stick to it. So we have to put multiple sensors for detecting the wind direction and wind speed. So I cannot say, okay, the variation was close. No, still required a lot of work.
Great. And my final question, it's for Marwan actually. So Marwan, you were saying that in the systems where you had the fixed DO versus the ABAC, in the secondary part of that experiment, they would actually vary some of the amount of DO that they were adding. So what was the variation in the max DO adjustment that they were making in the ABAC versus the fixed DO system? And did that have any impact on a population of the nitrifying bacteria that you would see? Or was that measurement even done to see, was there an actual difference in the population size that could kind of feed back to, okay, well, now we're seeing a reduction in ammonia and conversion into nitrite and into nitrate? Sorry, and thank you for answering these questions, by the way.
Okay, thank you very much for bringing this up. Actually, I did not have a chance to go through this, but let me share my slides and I can show you exactly what we meant by that, and then I will answer your question about the population. Okay, so I did not have the chance to share this, but this is the actual profile for the ABAC. So the ABAC, it is changing. I would say it's an online sensor. It's changing all the way from up and down, up and down, up and down, but there is a limit for the system. There is a high limit and low limit. The system cannot go, for example, below, I would say 0.8 for mixing issues, and it cannot go up, I would say up of 3. So it has a limit, it's a software, but it goes up and down based on the feedback of the ammonia sensors at the beginning and at the end. So let's say at the beginning it's 40, so they will have a certain DO that's matched this specific ammonia loading rate. And at the end, if it's less than the limits they are allowing, so for example, in summertime, they have a limit of 5 milligram per liter. So if it's less than 5, they will just pass through and everything will be fine. If it goes up of 5, they will increase the aeration. Same thing, like it's up and down, up and down, up and down, but based on actual values. It's not just we are blowing the air without any like sense. So in high fixed DO, they are just fixing the aeration regardless whether you are having high or low ammonia. So you are basically over aerating. This is first thing. Second thing, does this affect the population? This is what we will know because I took samples for microbial analysis, and we are now doing the microbial community, and also in addition to the microbial community, we are doing the enzyme activity. So we are actually, we would know like if this bacteria is present, is it actually working or not? It's not the case that it's there. We need to know if it's actually active and it's doing their work or not. So we will know these. Thanks very much for bringing this up.
I can add something quick here, Robert, if we have a minute for Saad and other people who are really, we call it low DO, but it's not low DO. So it's not the low DO that we know. Low DO when you go to 0.3 or below 0.5. The maximum low or the lowest point that we could go is 0.8 because of the compliance. And as you may know, if you're gonna go with low DO, low 0.8, you have to be careful because you're gonna have that spike ammonia at the end unless you change the SRT. So with changing the SRT, this is a lot of work from the operation perspective. So for this specific case, we asked, okay, can we go lower DO, which is to reach 0.5 or 0.3, but that will require a change or increasing the SRT. So, you know, reality is real. Said, no, we cannot go with that. But you have to be careful if you are going to test the low DO, you have to change the SRT.
Okay, thank you for that. So we have a few questions in the queue. Alan has already answered some of them through the chat, but the next question that had come up is in the Q&A, and that's from John Need. What are the next steps for integrating this research into standard wastewater operating procedures?
That's I would say a 1 million, not 1 million, 100 million question, because unfortunately what we experience now is that it's a site specific greenhouse gas emission. It's a site specific. You cannot really make it. But what we can come up at the end of this project, based on our experience, we can give some hints on what you should consider if you are going to monitor or measure the greenhouse gas emission in your site. As a general guideline, this is what our aim to get. So what you should consider, what are the points that you might not putting in your mind, it should be considered, but we cannot, based on our own experience in that one, we cannot generalize it for the facilities. Unfortunately, this is a case by case. It's completely different from the two campaigns that we worked with, from the different side that we are trying to collect the data and do even the greenhouse calculation using the OWC calculator. So it's specifically side by side, site specific case.
Thank you, Elsayed. And I know we're short on time. We'll just have one more question with a hand up. Elsayed, Mustafa, I've allowed your mic. Should be able to ask a question now. Elsayed, you had your hand up.
Maybe he's still muted, yeah.
Seems like he's here, but well, maybe it'll take a moment. We'll just check chat. There's no more questions there. There's more questions in the Q&A, but it's been a lively discussion. Elsayed, can you still hear us? Perhaps there's a mic issue.
Yeah, he has a mic issue.
Of course, you can get in touch.
You can, yeah, exactly.
Yes, of course, anybody here who has any further questions can get in touch with Elsayed and team. We linked everybody's profile as much as we could in the descriptions, but you can also reach out to myself, Robert Nyman, the Manager of Partnerships and Program at the Ontario Water Consortium, at Robert at ontariowater.ca, and we can always connect you with Elsayed and their team if you have any further questions. I think it was a great session. I think great presentations, Elsayed, Marwan, and Ahmed. I think we really appreciate you taking the time to discuss this important project, and we look forward to perhaps a second session in the future, talking on the modeling perspective. And thank you, everybody else, to the audience for being here and listening, and for your insightful questions. We look forward to seeing you again. Thank you very much, everybody.
Thank you.
Thanks.